Hi everybody, welcome to my 16th axial bar video. In this video, I'm going to be finding out how much point D moves down under the application of this load, and we're going to take into consideration that these rods holding it up are going through a temperature increase. If you want to know something else about axial bars, feel free to check out any of my other axial bar videos. So in order to find out how much delta D moves down, we're going to relate that to delta A and delta B. Alright, we can find delta A and delta B because we can find the normal forces in B and A. And then using the normal forces, we can find the displacement using delta equals NL over AE. Alright, so that first step then is going to be to find the normal forces. Okay, so we'll make a cut here, look down, cut here, look down, and get a free body diagram happening of that piece. Alright, so approximately like this, body diagram. The first step is we're going to have to find some sort of forces equation. So that's what we're doing now. So you can imagine we're going to have a reaction at C right there. We're going to have a normal force at B, normal force at A, and of course this 150 kilonewtons is still pulling down out over here. So taking our moments to be positive in this direction, we could find a moment equation for this. So it's going to be NB times this distance. We don't need to worry about this because there's no distance, so this doesn't contribute a moment. If we take moments about point C, moments about C is 0, so NB times the distance it acts, that's 1.5. Alright, plus NA times the distance it acts, 4 plus, so right, minus 150 times 10 to the 3 times the distance it acts, that's 5, equals 0. Quick rearrangement, 1.5 NB plus 4 NA equals 750 times 10 to the 3. Alright, this is our first equation. It's the result of taking a look at the forces. So we can see it's statistically indeterminate. We have two unknowns, and we have no other way to find any of the other unknowns by just looking at forces, moments, that type of thing. So we move into displacements. We need to look at the geometry of displacement of this quite closely. So the easiest way I find is to draw a clear picture of what the bar is doing beforehand and what the bar is looking like after it's gone through some of this twisting sort of action. Now you might have noticed I've drawn this here at like a 90 degrees, and you're probably thinking, well, if you have this beam and it's rotating, you know, between here and it's placed here, that's not 90 degrees. Well, we're going to assume that the delta is so small, so it's only moving like this much, that we can approximate that within 90 degrees. Alright, that makes it easy for us to use similar triangles. So the displacement of this point here is the displacement B. So we can say delta B. The displacement here, delta A. Alright, because that's how much this piece is going to move down. And of course the very end, this whole distance here, delta D. Alright, now using similar triangles, we need to have some dimensions here. And quick draw them back in, 1.5 meters, 2.5, 1.0. So the idea of similar triangles is, if you have a triangle that's similar, then the ratios of any of the side lengths are going to be the same in between each triangle. So we're going to take a ratio of the legs of the triangle here. So delta B by 1.5 equal to delta A by this whole length, 4, equal to delta D by this entire length here, that's 5. Alright, now if you notice in this equation here, we're only worried with A and B. So in order to find NA and B, we need only to worry about this piece of the equation. So let's just rewrite that. Delta A equals 8 delta B by 3. Alright, so this is our second equation. Now, this is displacement. Let's move into force displacement. Force displacement. Now here we have two considerations. Alright, because previously we've only had forces causing a displacement on these bars. But now we have an increase in temperature as well. That's also going to result in some displacement. So we have to take into account those two sources of displacement. So the one is, of course, delta is NL over AE. And the new one that we just introduced, delta, is alpha delta T L. So the displacement of any of these, so let's say the displacement of A is equal to the displacement of A from the thermal effects plus the displacement of A from the forces. So we can write this equation here in terms of each component of the displacement. So let's just do that. We can say delta A is just this, of course. Delta A temperature plus delta A normal equals 8/3 delta B. So it's going to be delta B is going to be increase in temperature. So we're going to have a displacement because of that. And of course there's going to be a force in there as well. Just like that. So this is only the really new part of this question compared to questions you've seen before. Is you need to include this thermal part in your displacement equations here. Alright, so we can rewrite these in terms of all the components of these equations, right? Because the thermal expansion of A is due to the properties of A that have to do with contributing toward that thermal expansion. Let's just do this a minute. NA LA over EAA, that's the normal part, plus alpha A delta T length of A, thermal part equals 8/3. Now we have the normal part of this one, that's NB LB EB AB plus alpha B delta T length of B. So this is the full and expanded form of our force displacement relationship. Now, I'm not going to go through it. You can plug all these values in over here. I had to spend time writing that big list down. But anyway, you plug them in and you get that NA equals 3/2 NB plus 15 times 10 to the 3. This is in newtons. Alright, we'll call this equation 3. Alright, we're going to take 3 now, turn it into 1. So essentially we've done what we did before in any of the other statistically indeterminate problems. We found an equation to do with the forces. Found the displacement equation. We plug the two into each other and solve. Alright, the only extra thing is we have some thermal effects to take into consideration here. Alright, we plug 3 into 1. 1.5 and B plus 4 times this whole mess here. 1.5 and B plus 15 times 10 to the 3 equals 750 times 10 to the 3. Alright, all good. And B equals NA equals, you know, once you find NB, you go back, you find NA. This is 92 times 10 to the 3 newtons. And NA 153 times 10 to the 3 newtons. Alright, so this is just kilonewtons, but we're going to leave it like this because displacement, we want to keep it all in terms of our fundamental units. Alright. So now that we have NB, NA, we really only needed one of those. Alright, and I'll show why. Because we know that delta D is equal to delta A by 4, and delta D is equal to delta B by 1.5. So really, we could just like say delta A is NL over AE plus the thermal effects, and then it's equal to delta D. So we really only needed to do normal A or normal B. But this way, you have some variety. All right, I'm just going to choose to use this one here. Delta D is equal to 5/4 delta A. So I'm choosing to use delta A. So therefore, delta D is 5/4 of course, delta A has a thermal component and a normal force component. So NA, LA, EA, AA plus alpha A, delta T, LA. Alright, you can go through, plug in these values. Now that we just previously solved for NA, we have everything that we need to solve for the total displacement of D. Turns out to be 10.6 millimeters. Alright, there we go. That's the answer for this question. So in a quick review, alright, the process is always more important than the answer, because the answer only works for one question, the process works all the time. So made sure we had an initially clear looking drawing, made a clear free body diagram, labeled all the forces, the directions, and that allowed us to find an equation that has consisted only of forces, or in this case moments, but moment is just a force at a distance. Then we looked at the displacements. We realized it was a sort of like a bar on a hinge, so we used similar triangles. Then we went to the force displacement relationship, and we realized that the displacement is not just because of the force. We now have a thermal component. So any displacement is going to be thermal displacement plus the normal force displacement. We related the two together, found an equation that related them all, plugged in our values. Now we have NA and B, and we have this equation, NA and B. Solved it simultaneously, found NA and B, and then we went back, used this displacement here, and found delta D to be 10.6 millimeters. Alright, hope this video helped you guys out somewhat, and we'll see you in the next video on axial bars.